Hi, I'm Alex, and today I'm excited to be sharing our work, Power on Touch, which was done at the University of Chicago. So let me show an interaction to illustrate what I mean by power on touch. So this user is typing his code into this keypad in order to unlock this locker. But this isn't an ordinary locker. You see, we've removed the batteries from the keypad, and yet it can still turn on and unlock, and can even actuate that unlocking mechanism. So let's watch that again and see how we power this on demand. The user wears our wireless power transmitter, which inductively powers the lock and keypad while the user interacts with it. When the locker opens, we can see that it's been retrofitted with this receiver coil and circuit. This is the key that lets us remove batteries from devices in order to power them on demand instead. Now, why are we so passionate about this whole business of battery-free devices? Removing batteries from devices enables scaling to powering many devices in the environment, since we no longer need to maintain batteries for every single individual device. And at the same time, our approach uniquely enables powering across a wide power spectrum and different varieties of touches. Back in 1991, Mark Weiser famously laid out his vision for ubiquitous computing, a future where computers are embedded onto nearly every object. And of course, all these computers need to somehow be powered. And today, we see that most small electronics are powered by batteries. Now, this is sufficient for a few devices in a room, but batteries quickly fall short of a scalable solution when we consider that nearly every object will need power, with potentially hundreds of devices and batteries per room, as Weiser initially envisioned. Now, there has been significant progress in the space of sustainable and intermittent computing, like this battery-free Game Boy that can harvest ambient energy and energy from user input, and only requires 11.5 𝜇Watts to play. This is around as much as a single sensor and under that of a cheap LED. But unfortunately, this approach doesn't translate to all devices. And what I mean by this is that there are these devices that need actuators, like motors, that operate on a very different part of the power spectrum than these low-power chips and displays. In fact, they require 10 to 100 times as much power. And unfortunately, there just isn't an intermittent schema to power these types of devices. And so the big challenge that we face is, how can we first enable a wide range of devices to be powered, from those requiring just microwatts to entire watts, and then enable scaling to many of these high-power devices in our environment. And finally, since our approach is based on touch, we need to ensure that our approach is robust to different variations of touch as well. So here we characterize a few of many related works that inspired us, categorized as follows: instrumented environments, body as wire, and encounter type, which each come with their own benefits and trade-offs. So instrumented environments add transmitters into the environment for powering devices in their vicinity. These excel at transmitting high power, like we want for actuation, but are difficult to scale since there are many environments that just simply can't be instrumented, like the outdoors and on the go. And so, to make wireless power transfer mobile, others have focused on transmitters that can send power directly through the skin. However, the amount of power that we can send through the skin is limited by the current, which unfortunately becomes painful much before we're able to do something like drive a motor. And so, to achieve mobility while potentially powering these higher power devices, this project here, Touch Power, used a glove instead of the skin. And when the glove's power and ground electrodes aligned with receiving electrodes during grasps, like holding a TV remote, the grasp device could be powered on. And while this approach is scalable and high power, it isn't robust to variations in touch, like any kind of misalignment between the electrodes, or things like single finger interactions or even hovering. And so to achieve all three goals of scale, power, and robustness, we built the system Power on Touch. So our approach is based on resonant inductive coupling, like you might find in your phone's charger. However, since our transmitter is a wearable device, our approach is on demand and instead couples upon touch interactions. And since we care about touch, we are placing these coils on the back of the hand and the fingernail in order to avoid covering up the parts of the body that we use to feel the world. And so, to ensure maximal efficiency through the thickness of the hands and the finger, we maximize the coupling between coils by hand tuning these parallel capacitor values for each coil. Additionally, each coil has its own natural frequency, where its frequency-dependent efficiency, or Q factor, will be the greatest. So here you can see plots of Q factor versus frequency, where there are these distinct spikes at the resonant frequencies. And this is where efficiency is maximized. And so to maximize the efficiency, we're always tuning our coil circuits and resonant frequencies and selecting for coils that have that high spike at resonance. And these are the steps that precisely enable us to power this wide range of objects and devices. And so we made this wearable wire power transmitter that runs off of a small battery, and this device transfers power to our custom battery-free receiver tags. And these tags feature a receiver coil, multiple rectifier circuits, and a supercapacitor for short-term energy storage. Additionally, we include a fast-booting microcontroller that handles our logic, like when to discharge that supercapacitor through these MOSFETs in order to power actuators and other high-power devices. So let's bring this implementation all together now. When the user touches the small coil that's attached to the tag, power gets transferred. And that's evidenced by this LED turning on. We can see that the microcontroller has booted up. And so our tags can convert devices to being battery-free. So let's see how this user converts their digital calipers to being powered on touch using this tag. So first, the user goes ahead and removes the battery from the calipers. Bye-bye. Then they solder connections between the tag and the caliper's battery connector, so that now when the user touches the calipers, they power on. So we performed 5 technical evaluations that focused on metrics like efficiency and robustness to misalignment, and you can find the details of these in our paper or chatting with me during demo sessions. And what I'll present here is a small portion of evaluating interacting with a real device. So this is a TV remote that we've retrofitted with a receiver tag, 2 coils, and a vibration motor. We wanted to study how well we could power the remote, both using likely touches and less likely alternative touches, which were informed by this heat map data set. And so when a button on this remote gets pressed, it consumes bursts of power shown here, with the peak being around 34 𝜇Watts. And we can plot that peak power here as a threshold of when the remote can turn on. When we measured the average received power in each of these 2 touch scenarios, we can see that the received power is greater than the threshold in both of the cases, which demonstrates an instance of being robust to different types of touch. And finally, we can plot what happens when a user grabs a completely dead remote. As shown, the supercapacitor charges up and the microcontroller boots up in about 2 seconds, followed by the remote being able to send signals. And moreover, what's exciting here is that since there's excess power, we can even power up that vibration motor to provide tactile feedback and notifications while the remote is held. So we made and tested 9 applications that illustrate the versatility of this approach. Here's a few. Here, a user wears a coil on their nail to power a service button in a restaurant. As their finger hovers on the button, it powers on and continues harvesting energy so that when they press it, it can let out an audible chirp and send a Bluetooth message to request service at their table. And since these buttons are battery-free, many can be deployed without charging or maintenance. And finally, this box opens right away when it's grabbed by the user. Of course, there's no battery inside, yet we can still power this motor that takes well over 1 watt. Now, there is a limitation to this work. The user still has to carry and maintain a battery within their transmitter. And you're probably asking, who is going to want to lug around a battery with them all day long? Well, we all already are. We have our phones and our watches and even glasses. And the good news is that a lot more people than just me have been thinking about the burden of batteries and coming up with really clever approaches to moving energy around. And so there's this whole energy economy that's starting to emerge for devices to harvest and exchange energy. And what I'm really excited about is that these approaches all work in conjunction with and complement power on touch, where power on touch can charge its battery through harvesting or sharing power and transfer power back into devices in the environment entirely on demand. And taken all together, this emerging ecosystem points to a future where energy can be much more fluid Battery maintenance is perhaps seamless, and with devices like Power on Touch, actuation can become ubiquitous. Thank you so much for your time, and I'm happy to take questions.
Thanks for the talk. Do we have any questions?
Hi, thanks for your talk, Alex. I'm reminded of Paul Morgan's work, Power Shake. Are you familiar with that?
Yeah.
In his work, he makes a big deal out of shielding people from EMF radiation. And
yes.
you're not.
Oh,
And I don't know anything about this. Well, I don't know as much about this as you do, so I'd like to hear your thoughts on that.
Okay, we're not shielding people from the EMF radiation, but we're using well below the limit of safety here. So we ran a variety of studies in order to see kind of what the amount of absorbed radiation is. And so you can see here, this is an experiment that we ran that's in the paper. Difference between the energy that's received between the coil being in air versus through the hand. And so the difference kind of implies how much energy is indeed being absorbed by the skin. And you can look at the amount of power that's being absorbed and divide it by the weight or the mass of the hand. That's kind of how the European Union makes these kinds of safety standards and gets some sense of the specific absorption rate. We're about 40 times below that limit that they specify. As you go to higher frequencies, this becomes more of an issue, especially with things like tissue heating, but we're not experiencing that at all.
Thank you.
One more question?
Yeah, thank you for the interesting talk. I tried the demo in the morning. It's very interesting. Just wondering, now you have this off-the-shelf, somehow flexible antenna which is attached on the back of the hand.
Mm-hmm.
I guess one future direction is to make it as a tattoo that can be pasted on the back of the hand. But then the deformation of the hand may deform the shape of the antenna. That may affect the resonancy of the signal. Would that affect the power transmission efficiency?
I see. Yes, for a typical coil, that's the case. As you start to do things like stretch it, in fact, we've made kinds of soft and stretchable coils from liquid metal that, as we did stretch, we could see changes in kind of where the resonant peak occurred. There was a Science Advances paper maybe like a month or two ago that looked at kind of finding stretch invariant resonant coils for wireless power specifically, and I'm super excited about that work because that would actually make it so we don't have to do this kind of like dynamic matching. Let's talk offline, I can show you that.
Thank you.
Right, let's give applause to our last speaker.